In this video, we'll discuss double hashing, which effectively eliminates the clustering problem. We have seen linear probing and quadratic probing. And in both these techniques, we skip a constant amount each time. In double hashing, we'll skip a variable amount each time. And we'll do this by using a second hash function. This is the formula for double hashing. This is the first hash function and this is the second hash function. So we can see that here the increment factor is not constant. It depends on the key. Now if two keys are mapped to the same location by this first hash function, then it is not necessary that those two keys follow the same probe sequence, as was the case in linear probing or quadratic probing. Here the probe sequence for both the keys will be different because the increment factor will be different for both the keys. And this increment factor will be different because the value of this hash function will be different for both the keys. This was the probe sequence in linear probing. This was the probe sequence in quadratic probing. And this will be the probe sequence in double hashing. So we can see that the increment factors in both linear probing and quadratic probing are key independent. They don't depend on the key. While in double hashing, increment factors are key dependent. This is named double hashing because we are using two hash functions here. The first hash function is called primary hash function and the second hash function is called secondary hash function. An example of secondary hash function is this. Here R is a number smaller than the table size and is a prime number. Now we'll see some examples of inserting keys in a hash table of size 11 using this double hashing. We'll use this simple hash function as the first hash function and this one as the second hash function. Now first we have to insert this key 43. It is mapped to location 10. It is empty, so we insert it here. Next we have to insert this key 50. It is mapped to location 6, which is empty, so we insert it here. Next we have this key 57. It is mapped to location 2, which is empty, so we insert it here. Now we have to insert this key 61. It is mapped to location 6, which is already occupied. So now using the double hashing formula, we calculate the next probe location. And this is how we do it. This is the value given by the first hash function. This is the second hash function. 7 minus key mod 7. And the value of I is 1. And here we are doing mod table size. So we get location 8 and it is empty. So we'll insert this key 61 at location 8. Now we have to insert this key 68. It is mapped to location 2, which is already occupied. So we calculate the next probe location. It comes out to be 4 and this location 4 is empty. So we insert the key 68 here. Now we have to insert this key 30. It is mapped to location 8, which is already occupied. So we calculate the next probe location. It comes out to be 2. But location 2 is also occupied. So we calculate the next location. And this time value of I is 2. Now this next location comes out to be 7. This location 7 is empty. So we insert this key 30 at location 7. So this is how we insert the keys. Now in double hashing, there is no problem of primary or secondary clustering. This is because the keys that have same initial hash address probe different sequence of locations. For example, these keys 46, 35 and 57 all are mapped to the same hash address 2, by the primary hash function, but the probe sequences are different. While in linear probing and quadratic probing, the probe sequences for keys mapped to same address are same. So here we can see that all keys mapped to location 2 have this probe sequence, and here all keys mapped to this location 2 have this probe sequence. Now let's talk about the choice of hash functions in double hashing. The primary hash function is chosen as usual, but we should keep some things in mind while choosing the secondary hash function. Firstly, it should not be the same as the primary hash function. And second, it should never evaluate to 0. If it evaluates to 0, then the probe sequence will always remain at the initial hash address. This is the formula for calculating the probe sequences. Now here, if this value is 0, then we'll be stuck at this hash address only. Now value given by secondary hash function should be relatively prime to the table size. That is, their greatest common divisor should be 1. If this is so, we'll be able to probe the entire table. The probe sequences will visit all of the table locations. If they are not relatively prime, then there will be slots that would remain unexamined. Generally, the table size is taken as a prime number, so it will be relatively prime to all step sizes. As we have seen before, a good choice for secondary hash function is this, where r is a prime number less than the table size. This double hashing eliminates the clustering problem, but it is more complex and slower than linear and quadratic probing because it requires evaluation of 2 hash functions. So we have discussed 3 forms of open addressing techniques: linear probing, quadratic probing, and double hashing. We have seen that the load factor of a table is defined as the number of records divided by the size of the hash table, and it is generally denoted by this lambda symbol. In open addressing techniques, the load factor is always less than 1, as the number of records cannot exceed the size of the table. For better efficiency, it is desirable that there are always some empty locations inside the table. So the size of the table should be little more than the number of actual records to be stored. If the load factor of a hash table becomes close to value 1, it means that the hash table has become dense. There are many occupied locations and very few empty locations. So there will be more chances of collision and the efficiency will reduce. So as the table approaches maximum capacity, load factor approaches 1 and searching becomes linear. The only solution to this problem is rehashing. In rehashing, we take a new hash table of larger size and hash all the entries to this new hash table. So leaving some locations empty in the hash table improves search time but results in a wastage of space. Therefore, we can say that it is a space versus time trade-off.